Friends, so far we have studied the slope deflection method. Now we will study the moment distribution method. The moment distribution method was developed by Professor Hardy Cross in the year 1930. It was popular. Today, now we are in the computer aged civilization. Even in this age of computer, the method is helpful in the preliminary designs of structures and in checking the computer results. Lot of softwares are available in market. We can compare the results of the softwares with the result got by the moment distribution method. Here first we have to know the basic things in this basic ideas, that is preliminary ideas. Here first we have to consider a cantilever, proper cantilever beam, moment and rotation of a proper cantilever beam. Here if you apply the clockwise moment MA at A, the values of theta A, here this one is the proper cantilever beam. Here if it is subjected to a clockwise moment MA at the proper end, it is subjected to MA. Here it will undergo deformation like this. Here this is the slope at the proper end. Here this one is the fixed end. The slope is 0. It is Then this one is the resisting moment. This one is the resisting force or the reaction at fixed end. This one is the reaction at proper end. Here now we want to find the theta A, that is slope at A, due to the applied moment MA at proper end. Then we have to take the separate beams. One is the simply supported beam subjected to moment MA at A. Similarly, another one is the summation of these two, that is another one is subjected to moment at B. Then they will undergo deformation. Here MA is clockwise, it will undergo deformation like this. Similarly, MB is clockwise, the deformation is like this. Here this one is theta A1, this one is theta B1, this one is theta A2 due to the moment at B, this one is theta B2 due to moment at B. Here the beam subjected to MA, here the beam subjected to MB. Now we can calculate these deformations, angular deformations, by using the conjugate beam method we have studied. Here this one is the conjugate beam method. Here we have applied MA. Then by conjugate beam method, you know that the shear force at any section in the conjugate beam is equal to the slope at that point in the given original beam. Here this one is MA, the moment is sagging, hence this one is RA dash, this one is RA dash. By conjugate beam, in beam A dash B dash, theta A1 equals shear force at A dash as per the conjugate beam theorem number 1. Then RA dash, that is, you know that the sign convention, left upward forces for shear forces, left upward is positive. Here the summation of all the forces to the left side, that is positive. Then shear force is RA dash, that is MAL by 3 EI. Then similarly theta B1 equals the slope at point B1, that one equals due to MA, that one is given by SF at B dash. Here this one is the upward, right upward is negative, hence that is minus RB dash. The shear force at B dash is RB dash minus RB dash, that one is ML by 6 EI. Now similarly to calculate theta A2 and B2 in the conjugate beam A dash, A double dash, B double dash, this one is, here this one is hogging moment, hence this one is the conjugate beam for this one, this is the loading. Here by conjugate beam A dash, A double dash, B double dash, theta A2 equals shear force at A double dash. Here this reaction is downward, left upward is positive, but this one is downward, hence that is RA dash equals, that is SF at A double dash equals minus RA double dash, that one is minus MBL by 6 EI. Here MB is the moment applied at B. Similarly theta B2, this one equals SF at B double dash, that one is plus RB double dash. Since the shear force is left upward is positive, right downward is positive. This one is downward, hence that is RB dash equals MBL by 3 EI. Then theta A equals, by observing these two figures, theta A equals the summation of theta A1 and theta A2. By adding these two, that is theta A1 RA dash, that one is MAL by 3 EI. This one is theta A2, that is negative, that one is MBL by 6 EI. Here by adding these two, here you will get an equation MAL by 3 EI minus MBL by 6 EI. That one equals theta A. Here by observing this original diagram, this one is the fixed end, at fixed end theta B is 0. Therefore theta B1 plus theta B2 equals theta B, that equals 0. Therefore by adding these two, that is one is anti-clockwise, one is negative, that is theta B1 is minus MAL, that one is MAL by 6 EI, MAL by 6 EI plus theta B2, that is MBL by 3 AI. By using these two equations, here by equation 2, we will get MB equals MA by 2. Similarly, by substituting the value of this MA in equation 1, we will get MA equals 4 EI theta A by L. Here, by using this, we will get the MA, that is moment at A, and the theta A equals, that is we will get the value like this. Then if the rotation at end A equals 1, that is unity, then MA equals 4 EI by L. This term in equation 2, this is known as stiffness factor. This one is known as stiffness factor. That one is known as stiffness factor and is denoted by, usually it is denoted by K. In moment distribution method, first we have to calculate the stiffness factor. It can be defined as the moment required for, it is the moment required for, it is the moment required, the stiffness factor can be defined as the moment required for unit rotation of the near end. Unit rotation of the near end. In the above equation, theta A equals 1, then MA equals 4 EI by L, that is denoted by K. Then that is known as stiffness factor. That stiffness factor can be defined as the moment required for unit rotation of the near end, when the near end is simply supported and the far end is fixed. Here the near end is simply supported and far end is fixed. The stiffness factor is K equals 4 EI by L. Then this MB equals, by equation 1, MB equals MA by 2. Here by observing this, when the moment is applied at A, when the moment is applied at near end A, that is MA, the moment induced at the far end is half of MA. Here by observing this equation 1, if you apply a moment at moment MA at A, then the moment induced at the far end MB is MA by 2. That one is, here by observing these two, both MA and MB are of same direction. Here we have applied MA in clockwise direction, MB is also clockwise, and this term is, that is the factor half, is known as carryover factor. That is known as carryover factor. Here in this moment distribution method, we will consider the clockwise moments as positive and anti-clockwise moments as negative. Similarly, when you know when the near end is simply supported and far end is fixed, the stiffness factor K equals, that is 4 EI by L. Similarly, the rotation carryover factor, that one is 50% of the moment is carried from near end to far end. That is carryover factor with same sign. Then the stiffness factor at near end when the far end is hinged. Here in this figure, this one is a B, the far end B is hinged, and here, by using the same procedure, we can calculate theta A, that is theta A is SF at A dash in conjugate B, that 1 equals RA dash, that 1 equals left upward is positive, that is shear force at A dash in conjugate B. Hence, RA dash equals MA L by 3EI or MA equals 3EI by L when theta A is windy. Here MB equals 0. MB equals 0 since that is hinged. Thus the stiffness factor at near end when the far end is hinged, it is 3/4 of that when the far end is hinged. Here when the far end is fixed, the stiffness factor K equals 4EI by L. If the far end is hinged or roller or simple support, then K equals 3/4 of 4EI by L, or that is directly you can take 3EI by L when the far end is hinged. When the far end is fixed, 4EI by L. When the far end is hinged or roller or simple, then that is K equals 3EI by L. This we have to know before going to study the moment distribution method.